Paleontology, a science geared towards small children, focused on digging up dinosaurs while sporting a Jurassic Park costume. Skulls are popped out of the ground and put on display for public gawking. The relevance of this, beyond clickbait, coloring books, and monster movies, is unknown. No, wait. That's not paleontology at all. Paleontology is nothing less than the study of past life, all past life, from ancestors to alien forms. It involves fundamental questions like, who are we, and how did we get here, using the broadest possible definition of we, life itself. Dinosaurs, a category of birds, are just a small percentage of that. Yet they get the most media attention. It's a very accurate meme. Okay, I didn't even make this one. This is just the truth. Anyway, most of us paleontologists consider dinosaurs to be a gateway drug. There is so much cooler stuff in the fossil record, and we know so much about it. Let's go on a brief dinosaur-free tour of the last 4 billion years. First up, genetic material. Viruses, basically, started producing proteins and wrecking their environment. The Earth was infected with life. Some of these new bacteria learned how to eat sunshine, producing oxygen, pulling in carbon from the air, and destroying the iron food of other microbes by turning it into rust. This went on for billions of years. Some bacteria consumed other bacteria, gaining their power to turn oxygen into energy, becoming the precursors of animals and plants. But as a result, there were climate shocks, from hot to cold and back again, which ended up turning the Earth into a snowball covered with glaciers. The technical term for this time period is snowball Earth. 700, 800 million years ago. Anyway, microbes banded together, creating multicellular life. 600 million years ago, geometric colonies appeared, sucking microbes from the water. These were soon replaced by the ancestors of modern animals, the Cambrian explosion. Lobster relatives ate other animals, capturing them using their grasping arms. Armored, wriggling clamworms crawled across the seafloor and into it, creating new ecosystems. Our tadpole-like ancestors flitted along ancient coastlines, while their eel-like relatives with gnashing throat teeth swam above the ice cream cone corals of the first reefs, dodging school bus-sized krakens and hungry sea scorpions. Plant fungus came onto land, but then the glaciers returned, killing pretty much everything. But mass extinctions opened opportunities. Jawless fishes invaded the ocean, sporting points, prongs, and finally fins. Spiders, scorpions, snails, and worms came onto land. Somewhere around China, a fish developed jaws, and its descendants drove jawless fishes, sea scorpions, and branching plankton to extinction. Some of these fishes, which had arm bones in their fins, sprouted fingers, 7 or 8 per flipper. On land, plants became trees, growing massive, or spreading their spores only once before dying. But then the glaciers came back again, and it was mass extinction number 2. It was the age of weird fishes and plated sea lilies. Sharks with wings, sharks with buzzsaw jaws, sharks with fins covered in tiny teeth, sharks with crushing tooth plates, bony fishes that looked like modern angelfish and eels for the first time. Wetlands developed, sporting 10-foot-long millipedes and giant dragonflies. These spread across the supercontinent of Pangaea and died, creating coal, leading to a 100-million-year ice age. Finally, vertebrates made it onto land on a permanent basis, leading to alligator-like amphibians and saber-toothed proto-mammals. But then volcanoes erupted all over Siberia, everything almost died, and it was mass extinction number 3. The day life nearly died. A single, lonely, tusked mammal survived and thrived, but it was soon replaced by galloping crocodiles. In the ocean, marine reptiles, giant rafts made of the living relatives of sea urchins, and armored squids, ammonoids, of every kind and form. But then Pangaea started to split apart, forming a sea of lava that would one day become the Atlantic Ocean, spewing toxic gas into the atmosphere and mass extinction number 4. Yeah, there's actually a lot more than these 5. These are the big ones. So, finally, there were whale-sized fishes, and modern fishes mobbed corals, made gigantic by using their captured algae to eat sunshine. Crabs, stingrays, and other fishes with crushing teeth appeared, smashing shells and leading to an arms race between predators and prey. There was an explosion of marine biodiversity. Mammals climbed trees, flew, and did a lot of other things that are seemingly sort of modern. They were feeding on the first flowers, pollinated by the first bees. There were ecological revolutions on land and at sea, leading to the modern world. Except that an asteroid hit Mexico, and then that triggered volcanoes on the other side of the world in India, and everything almost died again. But, there's always a but, because we're still here. Mammals arose from the ashes, became small under extreme heat, and then ever larger. There were palm trees and snakes in the Arctic. Predatory deer dogs frolicked along ancient rivers, while their relatives returned to the ocean to become the first otter-like whales. Not hyenas and other sort of carnivores were chased off by giant, long-necked rhinos. Everything at this point seems kind of familiar, but not really. In Antarctica, an ice age started, forming the first permanent polar ice cap in 200 million years. This dried out the rest of the world, but it allowed the rise of grasses, of rodents, of cats. Somewhere in Africa, an ape started walking across the new savanna. Oh, and there were giant saber-toothed salmon. I just have to mention that. So we know all of this happened, and so much more. How? Why? Paleontology is a thriving science at the intersection of multiple other fields and technologies. There is no bigger data than the fossil record, and we mine every bit of it. We use CAT scans, we use isotopes, we use genomes, we use robots, we use mathematical simulations, and all kinds of analytics. We maximize all of it so that we can understand the past and how evolution works. It also lets us make predictions for the future. What will happen after the next mass extinction? What weird things will show up? Will mammals get smaller again? Will there even be mammals? In sum, we have learned a lot about dinosaurs, but there's so much left to learn from the other 99.9% of things that have ever lived. And that's paleontology. Thank you.